coolest thing about that job is, I'm sure you guys who have taken chem lab and the bio labs here, you're always working in micro scale. So you've got 10 milliliters, maybe 100 milliliters on a good day of chemical. My first reaction there, we reacted 50 pounds of material, and we used 100 liters of solvent. So the reaction flasks are about this tall. So that's always fun. Felt like I was in the land of the giants my first day on the job. It's always cool to think about the other scales that are out there. You don't always work with pipettes and little tiny beakers. But after I worked there for 3 years, I started going to Drexel for the PhD program in chemistry in 2011. You can see a little bit of campus there behind me. So first, I'll talk about a little bit about graduate school, how it works, what goes on there, what you need to know about it. It's definitely something you want to start thinking about early, maybe not right now, but early on in your undergrad career. So usually if you go right for your PhD, you get some kind of an assistantship. That's the big perk, as opposed to going for your master's and then a doctorate. The assistantship will pay tuition for you, so I don't have to pay Drexel any money. They pay tuition for me. You get a stipend, so you get money in your pocket. They do call it a stipend, not a salary for a reason. You're not going to get rich going to grad school, but it's nice to get money in. You're not doing everything on loans. And normally you get some benefits. As you get older, health insurance will be a big concern, so that's definitely something a lot of grad schools offer. So once you take the assistantship, you have some responsibilities. Some of those include taking classes, teaching classes, and doing research. So a lot of people think PhD programs are 5 years. I don't want to take classes for 5 years. That sounds horrible, especially after undergrad and high school. You'd be in school or in classes forever. However, classes are only really the first year and a half to 2 years. After that, if there's a class that sounds interesting, you want to take it, you could, but you don't have to. And it's a lighter class load. Normally you take 3 classes per term, so you're only in class about 8 to 10 hours a week. The classes are a lot more relaxed than undergrad. The professors treat you like an adult. It's a nice little change sometimes from the undergrad. You've also got some kind of a cumulative exam during the first 2 years of your program, typically when you're done with classes. Those range from program to program. So at Drexel, we've got an exam a month. Your professors in the program will pick a topic, tell you the topic a week ahead of time. You go and take the test. It could be anything on that topic. And you've got to pass 5 exams before you fail 5 exams. So they expect you to fail a few. So that's a pretty intense part of the program. But once those are done, it's a lot of freedom. You don't have any real class requirements. The big part of why they pay you to come to school is they make you teach. So they've got a lot of students, they have a lot of classes to cover, and we're basically cheap labor for the university. So once you go to school, you'll have some big classes. At Drexel for Chem 101, we've got 1,200 students in that class for the fall. So they break it up into 5 lectures. There's still 200 to 300 students in each lecture. So obviously the students wouldn't get the attention they deserve. So we've got recitation sections. Those are 20 student sections. They meet once a week. We go over homework, problems that they went over in lecture, some things like that. And it's basically to get more one-on-one time for the students. So a lot of TAs will cover that. TA is teaching assistant. So that's basically anyone besides a PhD who's teaching the class. And the teaching responsibilities, they really vary. Sometimes I'll go in before the quarter. The professor will give me a sheet. He'll say week 1, these are the 6 problems you're going over. Week 2, you're doing these problems all the way through the end of the term. I had a class this quarter. It was a lab class. The guy gave me the 7 labs I was going to do. He said, come up with a teaching plan, come up with a grading plan, run the class. So that was a fun experience. And these teaching responsibilities are really valuable. After grad school, a lot of people want to go into academics. They want to be a college professor. You really need a lot of teaching experience before someone will hire you. The final part of grad school is research. This is definitely the most important part for the students. For the assistantships, they last at Drexel for 5 years. They'll guarantee you money for 5 years. Other schools, it's 4 to 6 years. And basically, to graduate with a PhD, you've got to write and defend a dissertation. So the written part is going to be 100 to 200 pages of all the research you've done while you were at school. That sounds a little scary, 200 pages. The oral part of it is even worse. So you've got a 1-hour presentation to the public. That's not bad. After that, they clear the room. It's you and 5 or 6 professors at your school. They ask you questions either about your research or about chemistry in general until they decide if you've passed or failed. They go on for hours. Pretty much everyone has a horror story about their thesis. People get through it though. It's a really valuable experience. It's a way to say, I went through that, I can do that for your future jobs. And you've also got to do some publishing before your thesis. Things that, like journals, presenting at conferences, some things like that. So next week I'll be in Minneapolis at a conference. This is my poster I'll be presenting. The type's too small, it's a really big poster. But just to give you an idea, this is definitely something an undergrad could put together for a conference after summer of research. The posters are a lot more relaxed than the papers. The papers are really strict. They have a lot of requirements to go through. But the poster, you just say, I want to do a poster on this topic. The conference will let you do that. If you're an undergrad, they love having undergrads present. It gets them more money from the government. It gets a feather in their cap. Universities love having undergrads present. They get to brag to students like you guys who are doing college tours. We've had this many undergrads present. So it's definitely something you guys can do in a few years. So with all these requirements, why would anyone bother? I guess the more pure reasons for doing this would be you get to do cutting edge research, you get to investigate the unknown. Everything we're researching is new science. It's not stuff in textbooks. We're not doing titrations on known acids. We're trying to figure out new things, come up with new techniques. We get to play with instruments probably worth more than your house. I have a key to the mass spec lab. Down there we've got an instrument that's, I think if we bought it new today it would be 300 grand. We got a new one up and running this summer. I think that's worth 500 grand. So I'm a 2-year grad student. I've got a key. I can do whatever the heck I want on that instrument as long as it works when I'm done. If I break it, I'll probably have some people yelling at me. But anything short of that, I get to work. And you also get to learn research. So any of you thinking about the sciences, you could definitely do the research science with just a bachelor's. But you're going to be working under a PhD chemist, PhD biologist. You're not going to get to pick the experiments you work on, lead the group. You really need a PhD to do that. So it's really valuable work experience going to grad school. And a little more practically, it's definitely more security for your job. So this is this month's labor board statistics. On the right, we've got unemployment, so we want that to be low. On the left, we've got money, so we want that to be high. So you can see as we go from bachelor's up to the doctoral degree, we've got more jobs and we make more money out of jobs. So that's definitely a nice perk. So as I said, I'm doing chemistry. My specialty is analytical chemistry. So analytical chemistry, any of the medical shows, medical testing, forensics, all the stuff they do on CSI, that's all analytical chemistry. Anything you buy, food, clothing, products, that's made on a large scale, it's got some quality control testing. So they're checking for contaminants. They're making sure the chemical levels are right for the foods or the clothing. A couple of years ago, there was a lot of big scares about metals in children's toys, like lead in pacifiers, things like that. That's all analytical chemistry. So basically, if we're doing an analytical chemistry experiment, we've got two types. That's qualitative and quantitative. So qualitative methods answer the question, what stuff is in our sample? What's there? So if I'm looking at my picture here, and I run a qualitative chemistry test on it, I get an answer back like, there are apples, there are bananas. It's not going to tell me how many there are, just if I have them or not. It could also tell me there are no pears. It could tell me what's not there. For quantitative methods, it answers the question, how much of that stuff is there? So I would get an answer like, there are 3 apples, there are 3 red apples. I can have more specific tests, things like that. So we either want to see if stuff is there, or how much stuff is there. So the technique I've been studying is mass spectrometry. So that tells us the mass of chemicals in a sample. Now, it doesn't tell us, like if we've got a sample of sugar, it doesn't say we've got 15 grams of sugar in our sample. It tells us the mass of 1 molecule of that sugar. So it'll tell us it's 60 Dalton, something like that. So remember, all the masses I'm talking about are about 1 chemical. We're weighing 1 molecule at a time. It's a really powerful and really popular technique. I think on the CSI shows, they say run it through the GC a lot. That's a mass spec. A lot of medical testing these days, the research is in trying to get that onto a mass spec instead of doing spots in the lab or liquid tests. So with mass spec, we can learn about a chemical's identity, its structure, its presence, if it's there or not, and how much of it is there. It's a really big technique. There's a lot of money in it. A lot of companies are looking at it. So I said I've got a mass spec down the hall. I like to call this my mass spec, because not many other people run on it. So it doesn't look like it. That's probably worth $250,000 if you want to buy it new. This is the computer we use to control it. It's really easy to run. If one of you guys came, I could probably have you running samples in about an hour. The software made that a lot easier. But it's a really powerful instrument. So if we're going to do mass spec on something, there are really 3 steps. We've got to ionize our analyte. We have to put a charge on it. We've got to separate the ions. So we want to get all the ions that are 200 Daltons over here, all the ones that are 100 over here. That way we count them up when we do the detection. In detection, we basically just count our ions. There's a lot of different ways to do each step. That's why mass spec is a big field. Some ways will work great with proteins. Some ways won't work at all with proteins. That'll work great with small molecules. So there's a lot of specialization. There's a lot of specialized techniques for different applications. So as I said, we've got to ionize our analytes. To do any of the mass separations, we need to have a charge on them. Some ionization techniques are soft, and they're not going to damage the analyte. That's really good if we're trying to find out if a chemical is there. Let's say we do research, we find out that a certain chemical is present when someone's about to have a heart attack. It would be great if we could take a sample of their blood, run it through our mass spec, and see if a chemical of 1060 is there, 1060 mass. If it's there, we need to start treating them because they're about to have a heart attack. If it's not, we don't have to worry about that. So the one negative to that is if we've just got the total mass, it doesn't tell us what that molecule looks like. That's fine if we know what we're looking for. So here's a mass spectrum. For a mass spectrum, this axis is counts. So we're counting up how many ions we see. This axis is mass. So this is telling me there's nothing at 1052, all the way up to 1059. We've got no ions of that mass. We've got this many ions at 1060. We've got ions at 1061 and 1062. So this is actually the mass spec of one chemical. Anyone have a guess why we've got more than one peak? Okay, if I say that this one is all carbon 12, that's all carbon 13, or this is all carbon 12 except for one carbon 13 atom. Here I've got 2 carbon 13s. So we've got isotopes in the environment. It just so happens some of these molecules are a little heavier. We could separate that and see that on the mass spec. So here's the chemical that this is the mass spec of. You can see it's really complicated. It's a big protein. All the information we get is that it weighs 1060. We don't know anything about what it looks like. So that's one of the negatives where we just do this kind of ionization. Let's say someone walks down the hall. They say, I've got a bottle. The label fell off. I don't know what it is. I think it's expensive, so I don't want to throw it out. Tell me what it is. That wouldn't help us. If we know that something weighs 200, there's a lot of chemicals that weigh 200. So in that case, we're going to do a different kind of ionization. It's called electron impact ionization. It's exactly what it sounds like. I'm going to take an electron, smash it into my analyte. That's going to create a lot of fragments. So I've got an electron, slam it into my analyte. That's going to knock another electron out of the analyte. If I'm losing a negative charge, losing my electron, the analyte has to end up being positive. So you want to think of electrons as the glue that holds a molecule together. So some molecules are really stable. You can think of them like a block or a stack of Jenga blocks. I can take one block out, the tower still stands. I wouldn't get much fragmentation. The molecule is going to stay together. Other molecules are less stable. They're like a house of cards. I take away one card, the whole thing falls apart. So that would be a lot of fragmentation. So for this analyte that I drew, when I lose that one electron, it doesn't want to stay together. It's going to break up into little pieces. Some of those pieces will have charges. I can separate those in my mass spec. And that's going to tell us all about the structure. So here's another mass spectrum. We've got intensity over here again. That's how many times I see those masses. Mass down here. So here's our unknown chemical. I'm just going to go through real quick how we could get some structure out of this. It doesn't look like much right now. First thing I'm going to do is try and get the total mass. So I'm going to find my heaviest mass. That's at 106. I'm going to ignore this little peak here. That's from carbon-13. So I know my whole molecule has to weigh 106. I've got a big peak here at 105. That means I lost 1 Dalton from my total molecule. There's only one way we can lose 1 Dalton. That's losing a hydrogen. So I know there has to be hydrogen in this molecule that pops off really easily. The next thing I look at, if I go from my 106, my whole molecule, down to this big peak, that's a minus 28. If you look at the periodic table, there's really not much that weighs 28. We could basically have 2 nitrogens or a carbon and an oxygen. If you know a little bit of organic chemistry, you know that you usually don't have 2 nitrogens right next to each other. That's pretty rare. So I'm going to make a guess and say that that's going to be a carbon and an oxygen. I know that if I have a hydrogen that comes off easily, and a carbon and an oxygen, this is the kind of structure I'm going to see. So this is a common functional group. It's called an aldehyde. So those 2 peaks up there, actually the 3 peaks up there, told me I've probably got this in my molecule. So I think I got all the information I could out of the right side of the spectrum. I'm going to look at the rest of it. So if I look here, I see a peak at 77, some peaks right at 50, and just under 40. If I'm a decent mass spectrometrist, that's great. That's like a fingerprint. It tells me I've got this ring, 6 carbon ring. A lot of common structures are going to have really obvious patterns for fragmentation. Now, I couldn't tell you how this turns into these peaks. I just know from running a whole bunch of these kind of molecules, you always see those peaks. We don't really need to worry about the mechanism. So I think I've got this in my molecule. This weighs 77. My other piece weighs 29. If you add those up, you get 106. So we figured out our structure. Basically, we've accounted for all that mass. We've got benzaldehyde. So I go down the hall, tell my buddy, you got benzaldehyde. That's your chemical. Okay, so I said we can make these mass spectrum. We could ionize, but once we ionize, we just have a pile of ions, all different masses. So we've got to separate those somehow. We've got to sort them by mass. So the way we do that is, if we've got an ion, it's got an electrical charge on it. It's plus or minus 1. If we've got electric and magnetic fields, so if we've got a big magnet, or we've got metals with voltages applied to them, that's going to cause that electric charge to move. It's going to affect it. Just like if we throw a ball in the air, gravity pulls it down. We've got an electrical ion, or sorry, an electrically charged ion. Electric and magnetic fields are going to push it around. So if we set these fields up the right way, we can sort ions based on mass. Just going to go over time of flight a little bit. This is what I work on every day. So for time of flight mass spec, we give all ions the same kinetic energy. We basically give them all the same push. So you want to think of this as me pushing stuff. This is the formula for energy. Energy is 1/2 times the mass times the velocity or the speed squared. If I do a little algebra, I can rearrange it to look like this. If I get everything the same energy, the top is equal. My masses are different, so from the math, I know that my speeds are different. So again, think about this as me pushing stuff. If I've got a bowling ball on a table and a ping pong ball, I give them the same push. Ping pong ball is going to go really fast, right? It's got a low mass. It's going to move faster. Bowling ball's got a high mass. When I give that the same push I gave the ping pong ball, it's going to roll slower because it's heavier. So I'm going to do the same thing with my ions. So here, this guy's going to be our heavy ion. This guy's our light ion. This guy's in between. So I give all these the same push. This guy's heavy, he's going to move slow. This guy's fast, or this guy's small, he's going to move fast. I've got my detector down there. The detector is basically going to act like a stopwatch. When I give these a push, it's going to start timing. And it's able to see when the ions hit. So it's just going to wait, and when an ion hits, it's going to say, I saw 7 ions at 10 seconds. I saw 38 ions at 15 seconds. That's the way our detector's going to work. So we've got a little cartoon here. Time's going on, our ions are moving down the track. So you can see our fast ion got a lot farther. Our slow ion is lagging behind because they're moving with different speeds. If we go one more, our light ion hit our detector. Detector says, hey, I just saw some number of these ions. They took 4 seconds to get to me. Experiment keeps going. Time goes. Our middle ion gets there. The detector says, I just saw some more ions at 8 seconds. Same thing for a big ion. We just let time keep going. 16 seconds, it saw some more ions. Now, the detector doesn't know how much they weigh. It just knows how many they saw. So the way we get to mass is, I know my times. If something was moving fast, it's going to have a short time. If something was moving slow, it's going to have a high time. I can do a little physics and algebra, and then we get our masses. So to go through the whole process, heavy ion, it's going to be moving slower, so it has a higher time, and I know that means it's got a high mass. The opposite for the light guy. Light ion, it's going to move fast, short time, low mass. The new mass spectrometers, they're great. I don't have to worry about any of this. It's got computer programming. I just click a couple boxes, and it kicks out my masses. So that's time of flight. So I thought I'd talk about Drexel a little bit. Obviously, I like it. I chose to go there for grad school. To me, there's really 3 big perks for going to Drexel. One is that it's located in Philadelphia. That's great for culture, there's always something going on. There's bands, concerts, great sports teams, things like that. But also, for your academic and professional career, it's also really good. If there's an instrument that I don't have at Drexel that I want to do some experiments on, we've got the University of Penn, we've got Villanova, we've got St. Joe's nearby, tons of schools in Philly. So odds are somebody at Drexel knows somebody at Penn. They can give them a call, try and get me in the lab for an afternoon to get my data. That's really nice. I don't need to buy every instrument that I want to run on. I might only want to run 2 experiments. Also, there's tons of science companies in the Philadelphia area, all the way through the Delaware Valley. They know Drexel. They know Drexel produces good students. That helps you when you go in for a job interview. I know when I was looking for a job, it really helped that the company knew Penn State. They knew that Penn State puts out good chemistry majors. That's pretty much what got me moved up. The other thing about Drexel is that it runs on quarters. So most colleges run with semesters. So in the fall, you take 15 weeks worth of a class. In the spring, you take 15 weeks worth of new classes. Drexel has 3 semesters, basically. They're 10 weeks long. So you take 10 weeks in the fall, 10 weeks after Christmas, and then 10 weeks after that. So you get through 3 sets of classes a year. They are fast-paced. There's a lot of information in them. You got to keep up with the work, but it's great because you get in and out of your topics a lot quicker. Especially for the upper level stuff. You could take 1.5 times more classes than someone else at a semester at school. So you could really get a broader education. And they also really love co-ops. So co-op is like an internship, except it's got 2 great things about it. One is you get credit for it, so college credits. It replaces some classes you would have to take. 2 is you get paid for it. Most of the co-ops are paid at Drexel. Students usually make about 15 grand for 6 months. Trust me, that's great if you could pull down 15 grand while you're going to school. Put some money in your pocket, you could buy dinner sometime instead of just the dining halls. Really nice. And that really helps when you're applying for jobs. You've worked somewhere, you're not just some college kid coming out with no experience. You've got some real experience, you can have a good letter of recommendation. So that's a great opportunity. So here's Drexel's main hall. Really nice building, there's marble everywhere. That's where all the administrative offices are. A lot of classrooms are in there too. They, I think 3 years ago, opened a new athletic center. So tons of workout equipment, pools, basketball courts. They hosted the national championship squash tournament a year ago. So they got a ton of stuff going on there. And I have to put up our bio wall. We just opened a new bio building, and they've got a wall with plants on it. And before they opened the building, all we heard on campus was a brand new bio wall. So that's got to go in the presentation. I guess it's supposed to provide fresh oxygen for the building. I thought I'd wrap up and just give you a couple pieces of advice for the next couple of years. I know grad school is a long way off, but you definitely want to start thinking about it as an undergrad. So I would say visit campuses as often and as early as possible. I think there's a lot of sophomores in here. This summer, go to some college visits. I always knew I wanted to go away to school, but I went to, I think, the King's, Wilkes, and University of Scranton open houses. Just go there, get a feel for the way they work, Normally you get a free breakfast or a free lunch, so that's a nice little perk. They're usually giving you stuff too, t-shirts or hats, and you get to see the campus. You just get a feel for the way they work. And once you're deciding on a school, don't be afraid to visit it more than once. I think I went to Penn State 3 times before I committed. Once you're at school, get involved in research as soon as you can. Don't be afraid. Professors love to get free labor. They give you research credits, so that'll replace some classes you might need to take. Doesn't cost a professor a dime. So, free labor, they love that. And it's not just science work. So, if you've done newspaper or journalism here, you know how to lay out a page. They don't know how to lay out posters. I laid mine out. My professor came in and said, boy, that looks really nice. How do you make it look that nice? Just some things like that. People don't know. These guys are science guys, so they didn't always do this other stuff. If you could write a nice web page, some professors are older, they don't know how to make a nice web page. It looks like junk. So if you go in after a month of being in the group and say, hey, I can make this look really professional, really good, they love that. And get involved early. Sophomores can definitely contribute to lab groups. It seems like you'll never understand some of this stuff, but it's really not broad topics people are looking at. They're really small and specific. So if you just spend a couple weeks reading the papers the group's been doing, you'll understand them. It's not about understanding everything at once. You just do a little bit at a time, and all of a sudden you know what you're talking about. I said before, poster presentations are great. If you're applying to grad school or for a job, if you give them a PDF, say, I did this work, I came up with the question, I did the experiments, worked up the data, laid it out, they love that. It shows you can finish a project, you can do something substantial. So definitely think about poster presentations. Like I said, schools love it, conferences love having undergrads. And if there's one thing you take away from today, it's get involved in research early. Industry, grad school, either way, research is a great way to build up your resume. People love seeing that. So I'd like to thank everyone for their attention, and I can answer any questions about anything. Yeah.
What did you major in when you went to Penn State?
Chemistry.
Now, and you worked for a company for 3 years?
Yep.
Now, what made you decide to go on grad school?
I always wanted to do grad school. Towards the end of undergrad, I was just tired of being in college. It sounds weird to say. I'm sure Mr. Tasker or Mrs. Wills are saying, what's he talking about? But I was just tired of the grind of college. I wanted to make a little money. So I planned to work there for a couple of years and then reapply and go back to grad school.
If you didn't go on to grad school, would you have felt comfortable with your life as it was with that job?
If I had to do that job for 10 years, no way. If you're a tech in a lab, your job is in a production company to make the same product every day. So you want to do everything the same. You want to do everything as well as you can. But if you do something a little different, the product's not going to be as good. So you just want to be as repetitious as possible. That's not really fun to do for a long time. I'll say it's a great job. I'm glad I had the experience. But like I said, if I had to do that for 10 years, I'd be looking for a new job. Yeah.
Did you make a lot of money?
I started at 40 grand at my job. And keep in mind, that was in Lewistown, Pennsylvania. That's outside of the middle of nowhere, in the middle of the state. So the cost of living was really low. I would say if you guys, one day you're looking for a job, keep that in mind. Because 40 grand in the middle of Pennsylvania is a lot different than 40 grand if you're living in Philadelphia. So. Anybody else?
Anybody else questions? All right, well, thank Mr. Malys.
Let me ask you guys a question real quick. Did you understand most of it? Completely over your heads? Some?
There's a AP chemistry in here, but then there's biology 1.
Okay.